Thanks for having me. I'm thrilled to be here. I want to do two things in this talk. I want to show you a little bit about the Microsoft effort in quantum computing. In particular, I want to talk a bit about Liquid, which is a quantum programming language. I understand that you guys had a tutorial earlier this week about Quipper, which is also a quantum programming language. So I'm going to show a little bit of code in F# in Liquid. Maybe give you a bit of a flavor of what that language is. But then I want to move on to a topic I'm personally very passionate about, which is reversible synthesis. So starting from a classical irreversible program, how can we generate quantum circuits, and how can we do that while optimizing space, so keeping the number of qubits small. That's the idea. Wanted to briefly mention our group. So Microsoft has been in the quantum computing space for more than 15 years, I think, like in the early 2000s, maybe even end 90s. It was started by Mike Friedman. He's now at Station Q in Santa Barbara. There's a sister group now in Redmond. That's the group I'm in. I'm Krista's Forest group. And we're mainly in Redmond, mainly working on programming languages, compilers, quantum circuit synthesis, and optimization. Whereas in Santa Barbara, it's mainly about the physics aspects, condensed matter theory, and that kind of stuff. And Microsoft sponsors also some experimental groups. There's no experimental research at Microsoft per se, but there are several groups sponsored. I think this is a picture of Charlie Marcus's setup in Copenhagen, and this is Leo Kovenhoven's quantum computer at Delft. Microsoft is betting on a technology called Majorana zero mode, which is a special way to build qubits from topologically protected systems. So ideally those systems, you don't need much error correction on them, but they haven't really scaled up so far. By the way, feel free to interrupt me and ask questions during the talk. I'm going to start by saying what Liquid is and what's the motivation behind it. So the goals are, it was basically starting out as a simulator. So what we wanted to have is a high-performance simulator for small quantum circuits. Obviously, you cannot handle scalable quantum circuits on a classical machine, right? It will kind of top out at some number of qubits, and that number is kind of small. But the question is, how far can you push it? So Dave Wecker implemented this Liquid tool and optimized it heavily. So he was very interested in implementing as large a simulation as possible. So how many bits can you do with Shor? How many bits can you do with a chemistry simulation? So that kind of stuff. But it then evolved into an actual full-fledged programming language. And the idea here is that, like, ultimately we'd like to have compilation also. We can express circuits. We'd like to be able to not only simulate them, but also ultimately compile them into a quantum target architecture. Okay, so and of course there will be many levels of, there will be many stages and many levels where you can do optimizations. The optimizations can be very different depending on what stage you're in. In the high level, there can be typical compiler optimizations. Maybe you can identify code that you never even execute, right? Dead code elimination, that kind of stuff. When you move further down the stack, you might find typical circuit techniques where you replace parts of the circuit where you know you can replace it with a cheaper circuit. That's a typical task a compiler does classically. And those things can also be done, ideally in a quantum case. And it exists, some tools exist already now, but I think a lot of work needs to be done in that area in particular. But the long-term view is that we'd like to be able to target real architectures. By real, I mean actual quantum computers. So the stack would roughly look like this. This is a very simplified picture of the world, but we'd ideally like to start with a quantum algorithm at the very top, right? And that would be very abstract. Hopefully the programmer doesn't have to think in terms of circuits at that level, or at least not very much, so that he or she can actually express the things like you're used to in classical programming, right? Classically, you don't think much about assembler code. Some people do, but most of the time you're not thinking about assembler code. And hopefully the same will be one day true for quantum algorithms. And then you would like to translate it into circuits, and then of course there are many stages. At some point you want to equip it with error protection. And ideally that would also be done by a compiler that optimizes for the code, for the geometry of the qubits, and all these things. Right? And they're all interesting technologically and engineering questions in that stack, right? But ideally we'd like to use compilers as much as possible to make these translations easy. And at the end, we would like to have an optimized quantum circuit. If you're interested in simulation, it would be nice to simulate them on classical machines, clusters, and so on. So there, a lot of stuff exists, a lot of infrastructure exists now. The hardware backend, our group is working on, so we're working with the experimental partners to actually make the compilation flow end-to-end. But there are a lot of challenges, obviously, in that to make that whole stack work. But there's progress. Ask me more about it later if you're interested. Oh yeah.
Is verification of algorithms and quantum logic also in scope for you?
Yeah, it's very much in scope. It's a poignant question though, because we cannot run stuff on a quantum machine yet, right? We don't have a scalable machine. So the question is, what can we do in absence of a quantum computer? How can we ascertain that things are correct? So we can simulate up to some sizes. What we can do if a computation is of a special type, say if it's just a stabilizer computation, you have actually a scalable simulator, so we can do testing. If the circuit is just a Toffoli network, so it has only reversible gates inside, so those gates will actually never produce a superposition, then a lot can be done. And I have some slides about an effort we have in our group currently about verification. So what we did is we took a piece of the compiler, which is called Revs, and I will say a little bit more what that is. And that Revs compiler, we did a verification in a formal proof system, that whatever that Revs does matches the specification of the program. It's still early stage because the language we can actually, the language that gets compiled is only a very small subset of the host language. It's really small, but we could make that proof. We could prove that whatever the compiler produces matches the specification. And it cleans up ancillas and that kind of stuff. Let me see, it's towards the end of the talk. I hope to get there. But of course, in general, making a quantum verification is a challenging task. It's even not clear what the right abstract interpretation of the program should be, where we could do the verification. So there are several questions here. Okay. So Liquid as a simulator or as a language, we chose F# as the host language. You heard about Quipper, and Quipper it's Haskell. Conceptually, those are very similar ideas. Both are functional languages. F# comes more from the OCaml family. But you have the same kind of benefits that you get from having a powerful host language like Haskell. F# has the whole .NET stack, the whole Microsoft libraries behind it. So you can use all those in your F# programs. But of course, it augments then the language by some keywords that are typically specifically quantum. There's a lot of optimizations built in. There's a highly optimized linear algebra package underlying it. There are also tricks implemented that allow you to sometimes chunk operations into bigger units. That helps a lot. It doesn't seem to make much sense initially, but if you want to really get simulations done on a classical machine, it's often not the best idea to just walk gate by gate through your circuit. It's often beneficial to group several gates into one bigger unitary, say an 8x8 unitary or 16x16. Especially if that's very sparse, it can help a lot to keep the cost down in your circuit. Question?
Do you use the GPU for the linear algebra?
You mean GPUs? No, that's not used. Clusters are used though. It nicely parallelizes to clusters with many nodes, but those are all like standard machines. It could potentially be put on a GPU cluster, but I don't think that they've did that yet. So there's an Azure version for it too, but for GPUs, we don't have stuff yet. More questions? Okay. There's also a simulator for stabilizer circuits, and that's basically patterned after the Aronson-Gottesman paper. They had a CHP simulator. It's very similar to that. That scales to thousands of qubits, as you don't need a full circuit and vector multiplication for that kind of stuff. It was released last year, end of last year, the publicly released version, so it's not open source completely. Many parts are open source, in particular the actual programs that they've implemented. But what's not open source is the core of the simulator. There you only get a DLL, and that DLL has a restriction, so I think it's 22 qubits you can only do in that simulator. But it's useful for doing for doing small simulations, and you can explore small algorithms that way. For the stabilizer simulator, there's no restrictions, and there's actually ideas to actually make it fully open, so you can go to the full power, which I think goes up to 30 realistically, but that has not been released yet. The 23 qubit version you can get from GitHub, and also there's a paper by Krista and Dave where they describe the architecture of Liquid. I just finished, by the way, I wanted to mention this. There was a coding challenge where students could use the system and implement some small programs and show how they use the system for their work, and there were really good entrants. And we had about 5 winners, I think, 1 main winner and a couple runner-ups. And they used Liquid for open system dynamic simulations, for instance, Markovian master equation simulations. There was a project about neural networks and Hamiltonian learning. That was pretty cool stuff. And you can look up on the Liquid website. You can look up the projects and the winners. This challenge. I hope there will be another challenge coming up, but it's not out yet. So this most simple program, arguably in the quantum world, is the kind of the quantum hello world program, would be teleportation. So how does that look like in Liquid? So first of all, in teleportation, you need to create an EPR pair. So how would you do that? Well, you could define a function EPR. It eats a register of qubits. Okay, so Q's is of type qubits, which is a list of qubits. And then creating an EPR state would be just apply H to Q's, and that is a single qubit operation. Q's is a register. By default, it just picks the first one it can be applied and applies it to it. Right? So it applies to qubit number 0, which is the top qubit. And then the next step would be a C naught, and it applies to the first qubits it can operate on. It's 2 qubit gate, so it takes 0 and 1. So you get basically that circuit. That's a function. It basically goes from Q's to unit, in case you're interested into the fundamentals. All the functions need to be from Q's to unit, and they kind of have the side effect of manipulating the underlying state. You can then, once you define such a function, you can render it, or you can simulate it, or you can export it into some formats. And there are many formats that are supported, for instance, CASM, but also other data structures are supported to export it into. The rest of the algorithm, of course, now we need to do the measurement in the Bell basis, right? So teleport would look like this. You would, let's first pick up all qubits except for the head, and then on these we create the EPR pair, right? So we run that function that we just defined, create an EPR pair on that tail, and then we do a C naught on the head and a Hadamard, and then we measure the first qubit in the tail, and we do a control X correction, so that's classical information now. And we do a measurement of the very first qubit, and we do control Z correction. Okay, so everything as you would expect it, as you would have expected. So this part here is the creation of the EPR pair, as in this circuit, right? This is when you run this, and then you have the C naught, the Hadamard, the measurements, and the corrections. Classical information is denoted by double lines, and classical control is also denoted by double lines. It's a very standard notation. I think you can find it already in Nielsen and Trung. And then, as I said, you can easily render stuff. You can simulate this. So if you simulate it, here's an example of a couple runs. I think they're like 8 or 10 runs, where a random state is created by doing a random rotation, and then you want to see that state gets teleported correctly. So that script just logs the input state and then the final state. And lo and behold, you always get the input state back, right? And here you see there were many different possible measurement results in that Bell basis measurement. More complex circuits, for instance, a cat state is very easy to create. You just do a Hadamard on the first qubit, right? And then you do a sequence of C naughts. What's nice about F# is it's not very dogmatic. It has imperative programming constructs. It has functional programming constructs. There are a lot of object-oriented constructs. So, but like you can easily do a for loop, for instance. I mean, you can also do for loops in Haskell, obviously, but it's very natural to do that stuff in F#. You just don't care. If you want to have a for loop, you just do a for loop. You don't have to program it recursively, and then you say, let's, for all qubits in the tail, do a C naught from that head node with a target in that qubit, and then let's measure them at the end. So if you want to apply an operator across all qubits, and it's the same operator, there's the so-called bow tie. It just does the same operator on qubits. So the effect of that, so the circuit would be this, obviously, right, the Hadamard here, followed by that cascades of C-naughts, followed by that whole cascades of measurement, and the effect will be that at the end of the day you only measure, when you simulate that, you only measure the all 0 strings and the all 1 strings, as you expected, right? Of course, that stuff will at some point top out because we're limited by classical simulation, right? But it's 10 qubit or so, not a problem at all. You can easily extend the language. It's made to be extensible. You can define your own gates. For instance, the C0 of course is a built-in gate, but if you were to define it yourself, you could define it as this. Like this, you would define a function. Again, it needs to take Q's, and then it produces a gate. And in that case, you can specify it, for instance, by the matrix elements. You can use sparse matrix types here. You don't have to specify the whole thing. You can just say what the non-zero elements are. And in that case, we have 4. And also there is support for equipping stuff with error correction. So if in that case, for instance, the teleportation circuit, if you would use the Steen code, it would go from 3 qubits to 3 times 721, but then you need the ancillas also to do the syndrome measurement, and I think then you end up with 27 qubits because you get 6 per each round of the error correction, so 21 plus 6. 27 qubits, and Dave did the simulations for that stuff too, and to show that actually you can do the teleportation in an error-corrected way. Also, Shor's algorithm has been implemented in that language. One of the first things that were done, it was implemented using the Beauregard method, in case you're interested in the details. In that method, what's nice about it is that you need only very few qubits. You need 2n plus 3 qubits if you have an n-bit number to do the adders. What's not so nice is that you need a lot of controlled rotations, and those rotations will be around very small angles. So for that, you then need another step to synthesize that. For the simulation, you don't need to do that, so that was kind of a shortcut there. But if you actually were to implement it in a fault-tolerant way, you would have to replace those small rotations by a fault-tolerant gate set. I have a slide about that, a little bit of a plug later in the deck. But in the simulation, that was done with controlled rotations around arbitrary rotations. And the program also looks, as you would expect it, you can kind of create those Fourier states that you need, and then the addition is basically just an integer addition. And the whole thing implements the modular addition. So Dave has done, the largest I think he has done was a 14-bit number, factoring 8,189, which has several millions of gates and took 30 days on a single machine. If you could parallelize that somehow, I think you could probably bring that down, but that's what he did. And that's also, I like that slide because it shows that it really matters on like what optimizations you implement in your simulator. So the first version of the simulator he implemented, of course it's exponential, right? But in the first implementation, even simulating a 9-bit number took a day. And then a lot of optimizations helped him to bring it down to just a few minutes. And for these large examples that he did, if you would have run it on a very slow simulator, it would have taken years. But he was able to bring it down to a couple of days, which I think is pretty cool. So what are the optimizations? So one thing that has been done is to reorder gates to make it more efficient in terms of memory. So if you have an operation, for instance, that looks like this, it's a tensor product of some unitary, right? And the unitary operates on the higher order bits, and on the lower order bits, it does just an identity, and then you apply it to a state vector. It's state vector of length 2 to the n. You apply that unitary. So you could, of course, now do just matrix vector on that operation. That would be perfectly viable, but that's slow. So it's much better if you reorder it. So reordering is just a permutation of the qubits, right? And for that, basically, you just have to remember the order you store the qubits, and you don't actually have to do that permutation. Just remember. And then you do that in that on that permuted vector, but in that way that you operate with the operator on the lower bits. That means that really in memory, it will be a block diagonal matrix operating on nicely arranged blocks. So you have then the benefit that those operations are faster, in particular because they're now cache local. Right? When you take a piece of your state vector and you you load it into memory, you only modify the same piece. That's much faster than poking around in memory, because we get many cache misses that way. So that alone helps a lot to speed things up. Okay, any more questions about that part? I kind of want to show one example where it really showed the benefit to do these things, where it helped to discover new algorithms. And then after that, I'm going to show you how we actually do synthesis, the gory details. Okay. So one example where it would help was chemistry. So it's the idea to simulate a Hamiltonian, which is a very powerful idea. Some people believe that's going to be the main application for a quantum computer one day, that just simulate other problems in physics. In particular, in chemistry, it's these type of Hamiltonians that describe the electronic structure of a molecule. Typically look like this, and they can be mapped then to a qubit system by doing transforms. So two very popular transforms are either the Jordan-Wigner or the Brabby-Kitaev transform. They translate them into a qubit system, and then you can simulate it. And our group has looked in great detail into these algorithms and tried to optimize them. It turns out that they are they're polynomial in a number of orbitals, but those polynomials are high degree. So they start out with something like degree 11, I think. If n is the number of orbitals, yeah, you get n to the 11, and that's very slow. If you have a problem, like a realistic problem where people actually care about, say paradoxin, it's a molecule used in a human body, for instance, for metabolic reactions. It's also used in like transport and photosynthesis. Understanding the ground state energy of that molecule, right? There's an algorithm, very well-known algorithm, basically phase estimation on top of the time evolution by that Hamiltonian. But you have to trotterize that, and that makes it very, very slow. But there are many ways you can actually do those kind of simulation of these many terms. There are many ways you can do the trotterization. The shortcuts you can do where you can you don't have to go to the worst case trotter number. You can sometimes get away with less trotter steps. And all these things together brought down the cost for simulating that from n to the 11 to something like n cubed. N cubed by n to the 4, so there's kind of, it lies somewhere in between, I think, because you have to take that term into account. But that's a big improvement, right? And where does liquid come into play in that work? Well, you can simulate very small molecules, right? Here you have, for instance, hydrogen fluoride or H2, H2O, and so on. These small molecules you can fully simulate using the system, and then you can get an idea how that scaling will be for the larger size molecules, right? Paradoxin will be far out here. We have no chance of simulating that. That's way too big. But the smaller molecules you can simulate, and then you can see a trend how that curve evolves. If you start with that n to the 11 algorithm, you get horrible scaling. Then as you make these algorithmic improvements, you get better scaling, and it allows you to do these things in just under a minute. Yeah.
Are the times on the slide how long it would run on the simulator or on the actual quantum computer?
No, this is all on the simulator. Okay. This is actually simulated. All these things here, for the small molecules, they are simulated. That's extrapolated. For the big molecules, it's extrapolated. That's not actually simulated. So that would take many, many, many thousand, I think it's like 1 billion years it would take, if you were to run it on the classical simulator.
But then with the green line, you can do it in 3.7 minutes?
Yes, you could.
For that molecule?
Yeah, you
on
could.
your simulator?
Well...
But didn't you just say it was classically intractable?
You know, I'm not sure if that's really paradoxin. I think it's a smaller molecule. Good point. I don't think they were able to do paradoxin. That's, I think, maybe a smaller molecule they were able to do.
What I thought the numbers were sort of using liquid to figure out how many gates you're going to need,
yes.
But then figuring out how long it would take on the actual...
Oh, yes, you're right. You're right. Yes, sorry, I messed that up. Yes, thanks, I stand corrected. That number is actually on the quantum computer. Thanks for pointing that out. Yes. Those simulations, though, they did on the classical machine. And on the quantum computer, even those small molecules would take, yeah, okay, great. Okay, cool. So let's move on to synthesis. So I'm going to show you a little bit about the reversible synthesis, but I want to start by saying what's kind of the high-level picture. So our target set is of course a universal gate set, and there are many choices here. A very popular one is Clifford and T. I think you all know what that gate set is. Right? T is the rotation 1 and omega 8, a diagonal gate, and you assume you have all the Clifford gates available. And there are many other choices. It's not clear from many of these other choices whether they're actually supported by a fault-tolerant gate set. A nice gate set would be the so-called V basis, which would have that as an underlying operation, which is also universal. And that's very, very tightly connected to quaternions. Basically, it generates a free group, so you don't have any relations in that group. But we don't know a fault-tolerant way of implementing that gate set. There's a nice synthesis algorithm, though, to synthesize that gate set. And many other gate sets, for instance, you could have like a 12th root here, or Fibonacci systems arise naturally from braiding. Fibonaccianians, they would have a very particular universal gate set, and there's also kind of an algorithm known how to synthesize into those. At the high level, you would go from quantum algorithm, right, an abstract quantum algorithm, down to the operation sequence, but that will go in many stages. So in the first stage, it will look like this: that you have some gates that are just single qubit rotations about some arbitrary axis and arbitrary angles, and there's some functions that might be just in a library. There might be other functions that you don't know a priori how to implement them. You might have a classical description of the function, and now you would like to generate a reversible circuit for that. So that's how I picture how the circuit will look like. Right? Many pieces, some pieces you get from libraries, other pieces you will have to synthesize on the fly. From classical code, other pieces you will have to synthesize the single qubit rotations. So this talk mainly about that, but as you probably know, like that's also an interesting problem, synthesizing single qubit rotations, finding kind of, for a given rotation, finding the sequence of, say, H's and T's, right? That's an interesting problem. And once you have that, you will want to include error correction, so you will implement those T's in a error-corrected way. Typically, there are several proposals how to do that. One popular method is to do distillation of certain states. Once you have them, you can teleport them into the circuit. You might have to do some corrections. But that's certainly a viable way to do then these T gates. And so there's a many layer process. That little inset here is about the cost of finding these sequences, or rather the length of the sequences that you can find. So if you want to approximate up to an angle, up to an error epsilon, the best known method scale is something like either between 4 log 1 of epsilon and 3 log 1 of epsilon. There was terrific work by Peter and Vadim Kluchnikov, Dmitry Masov, Mike Mosca. So they around the same time discovered that it's actually very beneficial to not do Solovay-Kitaev for these kind of tasks, for the single qubit rotation piece, but to have a number theoretic picture of that synthesis stage, starting with the target rotation and first rounding it off into an algebraic domain. So basically you round off your unitary into an exact representation where you're symbolic. Right? You work then with entries that are integers and these values you need to adjoin. And then once you have it in this form, there's actually an exact synthesis algorithm. You can express it into a finite length word over the HT gate set. And that can be actually found efficiently if you believe some number theoretic conjectures that are very plausible. So in practice, those things are lightning fast, they always work. It's not possible, to the best of my knowledge, to prove that they work, but it seems to work. And if you look at the kind of how dense these gates are that you can actually address, where you can solve the equations that you need to solve to make the synthesis, they're very densely distributed over the set of unitaries. Okay, it brings down the cost for the synthesis, so the length of the words that you produce, it brings it down from something like log 3 plus delta. I think there was a paper that did like 7 or something, down to just linear in log 1 of epsilon. And that's a really big deal. If you want to have precision of 10 to the minus 10 or so, which is not uncommon. For instance, for the chemistry applications, you definitely need that much. It would be absolutely deadly if you would scale with the third power or even worse. Okay, so switching gears, I'm going to talk now about reversible computing. How am I doing on time so far?
You've used about half of your time.
Okay, half the time. Perfect. Were there any questions about the arbitrary rotations and the setup in general? Okay, if not, then I'm going to talk about reversible computing now. First question is, why do we care at all? So who cares about reversible computing in the quantum world? So I have this plug here, which shows some applications. So one big application is in arithmetic. Many algorithms that we know of currently use arithmetic in one form or another. Most prominent example, certainly factoring, where you need to implement the modular exponentiation. It's kind of not a good example though, because in factoring you only need to multiply. To implement that modular exponentiation, you only need to multiply with a constant, right? All you need to do is pick a constant, implement the multiplication with that constant, modulo n, and you know at compile time what is n. You can pick your constant, and then you only have to do constant times x modulo n. And that's relatively easy. That's why all these papers kind of were there very early on in the field. Like in the 90s, people already knew how to do that kind of stuff in a very efficient way. What's much more challenging is to do generic arithmetic. So take two arbitrary values that can be quantum superposition, and do a modular addition, do modular multiplication, modular inverse. That stuff is much more challenging. Even to do like a Euclidean algorithm, you would have to do a Euclidean algorithm, basically to do an inverse. To do that, there is a paper that discusses it from the mid-2000s by Cruz and Salka, but it's much more involved than just a multiplication with a constant. So that's kind of, for me, it's kind of one of the driving things, implementing that arithmetic in a nice way and to do it space efficient. We would need that, for instance, if you want to implement the discrete logarithm algorithm for elliptic curve, breaking elliptic curve crypto. You would need to have generic arithmetic. You cannot get away with just multiplication by constants in that case. For HHL, which is the linear systems algorithm that I think you all are familiar with, you would need integer inverses or reciprocals. That's also non-trivial. So one way to do that is by doing a Newton-Raphson iteration and then kind of unrolling that classically and then making that reversible. That's one way. People have actually analyzed that. There was a paper by the people from Columbia University who analyzed that, kind of a nice paper. The benefit there is that you only need very few Newton steps because it converges very fast. But you need to keep around a lot of garbage memory to unroll the entire Newton iteration. So the question is there better methods? So people look into table lookup methods for that also, because we might get away with only a very small number of bits. And I had a paper with Nathan Weeb where we looked into some quantum way to do that, where we only need very few qubits, but the approximation is kind of the trade space there. The approximation is not that great. And also you kind of implement it in a purely quantum way. It's not easy to get the classical information out of the quantum rotation that you perform there. But kind of that, to summarize that area, it's sort of arithmetic question. Amplitude amplification in those type of algorithms, you typically have some kind of oracle. People usually call it oracle. It's maybe a misnomer because you will have a white box. You will have some description of a program that you need to implement, so then it's no longer an oracle. But you have to produce a circuit that implements it on a quantum computer. Kind of then you want to do your search or collision finding on top of that. Right? So you got to be able to implement those oracles. And probably, I wasn't here on Tuesday, but probably Peter mentioned that in Quipper there is already a very powerful method for that, for lifting kind of classical functions to the quantum domain. And I want to kind of talk a little bit about that next, kind of showing how these techniques work when you do so-called Bennett method, but how they can also be improved and how you can save space in those techniques. Okay, another area where you need reversible computing, and it's kind of unexpected. You think like for simulation, the only thing I ever need is walking my terms of my Hamiltonian, and then I do some kind of trottering. But actually, if you want to do it efficiently and in a scalable way, these modern techniques to do it, they will need simulation for sparse matrices, kind of your indexing of your matrix that you will have to do in superposition. For that, you will need some kind of reversible synthesis. And also if you were, and that's kind of fancy, I don't think that's going to be a near-term application, but you could even compute the terms of your Hamiltonian on the fly. So starting with the description of, say, the molecule, you could then compute those HPQRS terms that you need for the chemistry. You could compute those integrals that you would need to solve for them on the fly using reversible techniques. Okay, so I hope that kept you motivated, and I wanted to make that pointer to Quipper, because in Quipper you have an implementation already of these lifting steps, right, from a classical program to quantum program. So the target is to go, so here the target is to go to a universal classical gate set, right, a reversible gate set, and in contrast to the Clifford and T gate set. So all we want to do is translate into Toffoli, C0 and naught. That's my favorite gate set. I don't like so much multiply controlled gates, because I think you can hide a lot of complexity in that. I think it's the most fair way to break down everything into just Toffolis and C0s and naughts. And it's known that that's universal, so any even permutation you can write as a sequence of Toffoli, C0s and naughts. That was shown a long time ago. And the question then, of course, is how can we find these sequences starting from like an irreversible specification of a function. Say, if you have the NOR function, and you want to kind of find such a circuit that implements the NOR function, or any other function you can think of. How can you actually find them? How can you find them if you can express the function in some level, high-level language? Say classically, if you can express it in C or Python or in Haskell or whatever you. How can you then find these things? And how can we make it so that the programmer has the maximum ease doing that, right? Not thinking about this. And of course, can we trade time and space in a meaningful way in these tasks? Example, so here's F# code for carry ripple adder, very simple code. Just go through your kind of full adders. Each time you're threading through a carry, and then you update the carry. The result is always the XOR between the A's, the B's, and the carry, and then you update the carry and so on. It's an irreversible description of a carry ripple adder of 2 n-bit numbers. Can we start from a description like this and generate the Toffoli network automatically? That's the goal. If you would have control structures, say such as if then else, right? Here's a current example of some interest. Say suppose you have a program like this that would compute a variable APA detect whether your front wheel speed is greater than 0 and your rear wheel speed is 0. Then you set that variable to true. If it's true, then you do some other things, and if it's false, you do some other things. And then depending on those variables that you declared, you run your engine or whatever, right? Okay. Suppose you have a program like this. It's an if then else expression, and you wanted to make that reversible. How would you do that? Okay. And okay, in a concrete run, of course, you would go like this. Right? You would be in a particular branch, say you're in that branch and then you do this. But in quantum, things are in superposition, so you have, sometimes you go through that branch, sometimes you go through that branch. And the circuit has to be agnostic of that. The circuit cannot know the input, it has to work for all the inputs.
Are you saying if Volkswagen had used a quantum computer, they would have?
Well, I'm not making any claims here. But maybe this guy did. So how to do an if-then-else statement? So one simple way would be this. So you could compute that predicate that tells you whether you're in the one of the 2 branches, right? You could do that by a subroutine. Suppose we have already a reversible circuit for doing that. We could store the result in a bit, and then depending on whether that bit is 1, we would do A. If the bit is 0, we would do B. And then, of course, we would have to clean up all the garbage we might have allocated, all the stretch space. We would have to clean up, because if it's entangled with our result, we cannot leverage quantum benefits. So you have to run the inverse actually, and so that's kind of a generic construct how you could do an if-then-else statement, if-then-else expression. Of course, it's not so good because you have to add control to everything in A if you do it very naively. If you're lucky, you can exploit some substructures inside A. Maybe you have a conjugation or like a joint of something, right? Then you don't need to control all the gates in A, but generically you would have to. A better way that works sometimes, doesn't work generically, but if you are able to prepare an eigenstate of A and B, which you can actually if A and B are classical, if they're just reversible networks, the all one state is always an eigenstate, then that network is a very simple network that also implements the if-then-else statement. But here you don't need to control the boxes, and you can actually do them in parallel. The only additional cost you get is, well, you need more qubits here compared to the previous slide, right? You need kind of double the space because you're both executing both branches sort of in parallel, and then swapping the one you care about, you're swapping it in with these controlled swap gates. So the cost will be whatever you need here, but that's just constant depth. That's also constant depth, and then you have the same depth as you had before, the maximum depth of A and B, that will be your total depth. Then they get other ways you can think of. The kind of, yeah, I don't want to get into that too much, but there are several other ways you can think of where you also kind of don't need to control those, and those would work generically even if you're not able to create an eigenstate of the two operators, but they're even more costly in terms of the operations you need, right? And the qubits you need. You need even more qubits for that case. Okay, so if-then-else statements, if-then-else expressions, okay, one thing. But what happens if you don't have such an easy-to-handle control structure? If you have just a classical program that's given to you, how can you handle that? So suppose you're given a classical program already over a classical universal gate set, say in NAND gates or NOT gates and AND gates. Okay, so how can you do it? Well, there's a simple way. So so the obvious issue is that those are not reversible, right? That's pretty clear. So a simple way is to replace each irreversible gate by a reversible box, so that one of these output wires, or there could be a set of wires, holds the actual result of the computation. Okay, so we could do that very mechanically for each gate here. We could replace it by a reversible gate, and here we have an inverter. We don't even need to do anything, and so on. But if that's the AND gate, it would be the Toffoli gate. So then we get actually the actual result we care about. We get it as one of the outputs, but obviously many of these other qubits still hold intermediate values. And they cannot. If we want to use that in a composable way in a bigger circuit, they cannot hold any garbage, right? That will be entangled with the output. So Bennett's idea from the early 70s was to run such a computation forward. Right? Can happen in many stages, and those might depend causally on each other, so you have to do them in that order. But at the end, you then copy out a result and you undo all these stages. After you undo it, you can be sure that all these ancillas that you allocated for scratch space will be cleaned up. That's very, very nice because you get a nice structure. It's nice to compile that structure. Easy to do. But it has disadvantages. One disadvantage is it needs a lot of qubits. It needs as many qubits as you had gates. Right? It scales with the circuit size of the classical circuit. It also has the disadvantage that many of these qubits are just sitting around idle. Right? You touch them at some point, and then you don't touch them for a long time, and at the end you touch them again when you clean them up. Okay, so your circuit looks like a big V, where most of the V actually doesn't do anything. It's just at that rim stuff happens, and in the middle of the V, the qubits are just sitting around. So that's not good. It would be nicer to actually use that space in a more meaningful way. So conceptually there's a solution to this, the so-called Pebble games. Let me walk you through what the idea is. Basically, the idea is to clean up earlier, right? To clean up some part of the computation early, then reuse those qubits that you freed up And then if you, later on, you might have to recompute these values, but you kind of happily spent that cost of recomputing because you freed up so much memory earlier. Okay, so it can be kind of formalized in the notion of a Pebble game. And what that does is the following. So suppose you want to do a computation that runs in 4 stages, and they all depend on each other. It could be each stage could be just computing a bit, but it could also be a larger register. Right? It's just some unit, kind of 4 checkpoints in your program, and they depend on each other. We want to get to the last checkpoint, which will be the final result. And we want to use as few pebbles as possible. And putting a pebble means you allocate that. You perform the computation, you use quantum resources to do it, and then you kind of have used them up, and they're now, you cannot use them again, unless you free them up again by uncomputing stuff. Okay, so if you want to do four steps, a simple way to do it is you make the first computation. Could be as simple as just doing one Toffoli gate, could be some sub-computation, but you do that. Then you do the next one, you allocate more memory, you do the next one, and then you have the final result. You copy that out into some extra space, and then you unwind your computation. Right? To do that, you still have the result from stage 3 here. So using that, you can now uncompute all that stuff, right? Because you still remember this, you can uncompute 4. So, oh, sorry, 4 is actually our final result, uncompute 3. So if we still have 1, so we can uncompute 2. We still have we can always uncompute the first step because it didn't depend on anything. So in 7 steps, we could actually put a pebble on the last box. Okay? The question is that the best possible? Do you always need 4 pebbles to get to the last box, or can you do it with less? Turns out you can actually do it with 3. So to do it with 3, well, the first step is you don't have a choice. You have to put it on the first. And you can, whenever there's a pebble to the left of you, you can put a pebble, or if there's a pebble there, you can remove it. Right? So we could remove the pebble here, but that's pretty pointless. So the only thing really we can do is put a pebble at 2. Okay? And now we could now remove the pebble at 1, but it turns out the best thing to do is actually putting a pebble at 3. We can't go to 4 because we put a space limit of 3. So the question is, what can we do now? We could remove pebble number 1 or pebble number 2. If we remove pebble number 2, I think we get stuck. But if you remove 1, now you have that pebble. You can put it in 4, have the final result. We copy that. And now we can use the pebble at 2 to uncompute 3. We can put that pebble back into 1, uncompute 2, and then uncompute 1. As you see, it went a bit forward and backward a little bit. The sequence was slightly longer. Instead of 7 operations, we needed 9. But we were able to produce the pebble at the final output. Okay. So the question is now, if you have a sequence of n stages, how many pebbles do you actually need to do that? And the answer actually is quite surprising. So, thank you. So first of all, I'm not aware of a closed solution to that. I know just some extremal cases where extremal strategies. One extremal strategy would be Bennett's strategy, where you use a lot of memory, but you get through with very few steps. But there are also strategies that use an exponential number of steps, but they get very, very far. With only very few pebbles, they get you very, very far. And Manny Nil has done, he wrote a paper that's not very widely known, I think, in the mid-90s, where he analyzed this kind of game and showed and produced this table. Basically, it's produced by dynamic programming, that you want to find the optimal strategy. If you store all these intermediate optimal strategies, you know that your optimal overall strategy must go through them. And that way you can actually produce such a table quite efficiently. And we implemented that stuff. It really works nicely up to thousands of stages. You can find the best strategy for a given number of pebbles. The way to read the table is like this. So here's the number of steps you want to get into. In the previous case there were 4. Here's your limit on pebbles that you allow. Right? And then the entry in the box tells you how many steps you need to do in your program, in your sequence. So if you have 4 and you have 4 pebbles available, you've seen you get away with 7. But you can also get away with 9. If you have 3 pebbles, you can get away with 9. If you want to get to stage 4 and you only have 2 pebbles, then you can't do it. Then there's an infinity here. It's not possible to pebble 4 steps with only 2 pebbles. It's not possible. But interestingly, then what you see is this scaling here gets you really far. So with 6 pebbles, for instance, you can get very, very far. It even pops out the table here. I think you can get up to 160 or so. 160 steps with only 6 pebbles. And kind of that strategy is another extremal strategy that looks roughly like this. So this shows the pebbling strategy in time, right? So this shows you which qubits you allocated, you move on, then you have your final result that you keep, and then you uncompute the whole stuff. Okay. So you could also think of a strategy that keeps computing a little bit, then stores the immediate result, uncomputes, and so on. And an extremal strategy is that exponential strategy. It's also called the Lange-Mackenzie tap strategy. It gets kind of with only log n pebbles, gets you n steps far, but it has an exponential cost in terms of steps. If you plot it, that exponential strategy, kind of that shows you how many gates you need, so overall circuit depth. And width here, that's a bit of a misnomer. It means how many stages you have in your pebbling game. But you get very far with only very few pebbles, but then it tops out. Whereas Bennett is basically linear in the cost. A good trade-off seems to be not to go all the way to Bennett with an enormous number of pebbles, but to do something like 50 or so. It still looks almost linear, but you get very far. So the idea is to use those in a combination strategy. So these Pebble games, use them in a combination strategy for reversible synthesis. We have tried that in Revs. Revs is our kind of alternatives to the lifting monad. It's a reversible compiler. But we haven't really integrated yet full Pebble games. So we cannot really run arbitrary Pebble games on in our synthesis. One of the basic issues is that when you have a program and with a dependency graph, typically the dependency graph is not linear. You can always make it linear artificially by introducing checkpointing, but that's sort of inefficient in itself. I want to have something that's really efficient at the bit level. So starting from the dependency graph, I want to have something that just tells me which bits I need to compute. The problem now is that finding the best Pebble strategy on an arbitrary DAG, so directed acyclic graph, is not feasible. It's not feasible to do that. The problem actually is p-space complete to find the optimal pebbling strategy for an arbitrary DAG. If it's just a line, you're okay because then you can do these dynamic programming techniques. But if it's an arbitrary DAG, you can't do it. So what we did is we just implemented a heuristic, which seems to work fine in practice, in the case we looked at. But we can't prove anything, at least not yet. We can't prove anything about the quality we get there. Okay, so what we did is we, first of all, tried to use as much as possible in-place operations. That kind of goes against one of the very basic concepts of functional programming. We need to have immutable objects. Really, you want to work as much as possible, usually in functional programming, with immutable objects, because then you minimize errors that you could introduce. We go the opposite way. We say, hey, if we have mutable operations, here, for instance, if we mutate one of the registers and override it, that helps us a lot to save space. And an example is adders, but there are more examples. And you can actually manufacture in-place operations yourself. If you compute a function, for instance, right? You have a circuit for f. Suppose you have a circuit also for f inverse. So another circuit that looks exactly like this, only that you produce f inverse here. Then you can make an in-place update like this. You just need to kind of do f, and then you change the roles of the 2 registers and do f inverse. You have an in-place operation. So the idea is to use as much as possible these in-place operations. And then we have a data structure, we call it mutual dependency graph, which captures dependencies you might have between operations. Right? This operation, for instance, needs to input A, B, and then it also needs a place to store it. So it captures dependencies, but it also captures flow of the information that gets mutated during the algorithm. The flow information compilation is denoted by bold edges here, and dependency by dashed edges. So in that case, it will be just a Toffoli gate, but things can be much more complex. Here's an example where you have an OR function and an AND function, then you XOR them together. And that piece is just the OR function. It's a kind of a dependency graph that's classical for just the OR piece. And then to make it kind of reversible, we introduce some variables. They get mutated throughout the execution. Some of them are initialized clean and then end up clean. Some of them are actually output wires. And then you can actually put it all together. You have the OR function here, you have the AND function, compute the final result. And what you see is that sometimes it pays off to clean up things early. So the dependency graph analysis tells us which part of the circuit we can actually clean up early and then reuse them later in the circuit. So there's an algorithm which runs in quadratic time to find out that structure, that dependency graph structure. And some examples are, we used it to implement a cipher. So SHA-2 is a hash function. So what's nice about that is it has many rounds, 64 rounds in that implementation we looked at. And if you sort of do it in a straightforward Bennett way, the circuit size that you produce, partially fell apart here. The circuit size you produce will depend on the number of rounds, okay? Which is sort of surprising because a lot of the stuff can be done in place. So a lot of the things in the body of the cipher, thank you, in the body of the cipher just override the internal state of the cipher. Right? The cipher has an internal state that gets overwritten. So it would be really nice to leverage that in the quantum circuit that we generate. Right? So it would be nice if that circuit we generate does not depend on the number of rounds. And our tool is actually able to do that. So you can express that cipher in a classical way. So that's a classical implementation of the cipher. And now we can take that program, which we can compile into a classical executable. We did actually to check our results. But we can now also compile the same program into a Toffoli network. The round function of SHA looks roughly like this. You have like 8 registers. Each register has 32 bits. And then depending on what the values are of these registers, you compute some other function value and then replace those registers. It's a kind of cyclically shift, and then there's a very nonlinear dependence of that one register basically gets updated in a very nonlinear way. Everybody else gets just shifted. If you do that several times, all the output bits depend on the inputs in a very, very nonlinear way with a very high degree polynomial. Of course, like classically very easy to implement. That's how it was made. So quantumly we found that, so I'm not going to go into all these things, but they're all very simple functions. Quantumly what we did is we also synthesized by hand a circuit to implement the cipher. So we thought about like how would we do it, how can we save space and so on. And we found that we can actually indeed do it in a way that the overall cost in terms of qubits will not depend on the number of rounds of iterations we do. Okay, of course the circuit size depends, but the number of qubits doesn't. So the question is how close can we come to this hand-optimized circuit. So here's the data for the hand-optimized circuit. You see here the number of qubits and the Toffoli count. And you see here, if you do it just by Bennett, so you take the classical function, you unroll the entire loop, apply the Bennett method to that network of AND and NOT gates. What you see is that the number of qubits scales with the number of rounds, and of course the number of Toffolis also. This is just the time it takes to compile on a classical machine. If you do it with our method that we call eager, because it tries to clean up as early as possible, you see that the number of qubits we get here does not depend on the number of rounds. And that's exactly what we had in our hand-optimized implementation. We didn't quite get to the exact Toffoli count here. It's slightly worse for these large numbers, but we got pretty close to that. And that's completely automatically generated from the F# code. And by now we have more examples for functions. We also have benchmarks that we took from a benchmark website and implemented them in the language as Boolean functions basically, and compared to actually what was known in that library before, in that benchmark library. And oftentimes we found that we beat the circuits in terms of width, meaning a number of qubits. But for some cases, which I've denoted here in bold, we even are better in terms of number of qubits and in the circuit size using our tool. I wanted to mention at the end that simulating is always easy. So if you have just a Toffoli network, simulating on an arbitrary classical input is trivial because you just walk the gates and you update the state vector. I wanted to mention very briefly compiler verification. So our compiler, first of all, why do we care at all? Why verify? So suppose you have a structure like this, basic Bennett structure. You do circuit, you copy out, you do the inverse circuit, and you're kind of expecting that everything is clean here and the function has been computed. So how can we actually know that the compiler, while the compiler made these translations, how can we actually know that here on these bits we have the function and everything else is clean? It might look like a no-brainer, so because it has been made that way, right? We compute it, we uncompute it, it has to be clean. But if somebody gives you a network, and that's actually the output of that SHA function when you do just 2 rounds, instead of the 64, just do 2 rounds, get something like 350 qubits, thousands of gates, right? Somebody gives that to you and claims that implements the SHA function. How do you actually know that's true? Right? Because you can do testing, you can run some test vectors through the whole thing, but then you might not catch some corner cases. You might also not know for sure that all the bits are clean at the end. So what we did is we did verification of that compiler. So revs we turned into rever. Rever is a kind of an embodiment of revs implemented in a different language, where we could actually do automatic proofs of the correctness. What we lost in that translation was that we didn't get the full capabilities of revs. In particular, the space optimization capabilities are not fully expressed in that. We kind of have a space optimized synthesis here, but it just works with a symbolic representation of the output functions. It typically produces very big circuits. So what we need to do still is combining the mutually data dependency structure with the formal verification. So we did the verification of the basic Bennett strategy, and we did a space efficient strategy, but which in the worst case has exponential size circuits. But those are proved. So if you believe in the correctness of the F star system, which is an automatic proof system similar to COC, if you're familiar with the classical world, there's an automatic proof system called COC. So F star is very similar in that sense. It allows you to express programs and then reason about the correctness by giving lemmas. And if it all then compiles fine, then you can be sure that your program meets the specification that was given. And in our case, the program was the compiler itself, and the translations were the transition rules in the compiler. All right, that's all. Thanks a lot for your attention.
Thank you very much. Are there any questions or comments?
So towards the beginning, you mentioned that you implemented several optimizations in this liquid system. How many of those are needed to make this classical simulator go fast versus to make the compiled circuit?
That's a great question. The question is, in liquid, how many of these optimizations are actually specific to simulation, and how many are actually circuit optimizations? So it is more heavy on the simulation optimizations. So these tricks I showed you to reorder gates in memory. There are other tricks that they have done to make it faster, but they're typically for the simulator. It is known conceptually how to do, say, a technique like p-polling, which means you take a sub-circuit of your circuit and rewrite it by a simpler expression. But those haven't been implemented into liquid yet. It's one of the things I'm really passionate about. I want to get those things into liquid, but it's not there yet. So there will be actually a successor of liquid. It's called solid. It's what the group is now working on. In a solid framework, they are kind of, it provides a scaffolding for many of these optimizations that can then be plugged in. If somebody, for instance, implements p-pole optimization or resynthesis techniques. But right now, as of now, there's not much by that way.
Early on, you talked about the types a little bit, and you said that these circuits are, their type is from a list, I assume, of arbitrary length of
Right.
qubits to unit.
Right.
For one thing, is there any, you know, I would think of this as, you know, it's a function from qubits, some specific number of qubits to some specific number of qubits. Can
Right.
you specify length, and can you sort of talk a little bit about the types?
Basically, it needs to know the number of qubits. When you create the initial ket, sort of, you hand it a number of qubits. You say ket of 17, and you get 17 qubits. So it knows at that point how many qubits there are. When you specify the function, though, at that point you don't have to. You could do it basically you treat it as a list, but you could say, give me some number, give me an arbitrary length list, and do some stuff like a Hadamard and then do C0, that example, for instance. That's completely generic. You don't have to know the number of qubits. But when you instantiate, you have to give it the size of the state. And for that, you have to know the number of qubits.
So relatedly, can I, you know, it seemed, you know, looking at it, it seemed a little bit confusing because, you know, you're just applying a Hadamard to a list, and presumably when you do that diagram, you're just, you know,
Right.
ignoring all the ones that you're not operating on.
Right.
Can I either specify numerically or otherwise, you know, that it acts on individual qubits rather than as a list operation?
What you can do is you can specify a new gate and then say, I want to have that gate operate on 1/1625. If that's a 3-qubit gate, you have that much amount of fine control to say on which qubits you want to operate. The examples I showed, they were kind of not of that flavor. They were kind of, you just walk the list, right? But when you implement larger libraries, for instance, you will have actually need for exactly what you said, that you need a lot of the, you need to know how many qubits there are, and you know exactly where they are, and then operate on these qubits. So that's stuff I'm doing, for instance, right now, like libraries for modular arithmetic. And in those cases, I produce big networks. I have to know exactly which qubits I'm operating on. And a lot is then saying, okay, this qubit, this qubit, this qubit, let's do a Toffoli gate between them.
And you do that
I don't know if that answers the question.
Yeah, do you do that by just sort of...
Let's leave the follow-up
sure.
questions for the follow-up.
Yeah, I'll be around.
If there are no more questions, then we will thank Martin again. Thank you very much.